Okay, guys, good day, everybody, again. Welcome as we look at our lesson 4. Last week, you guys did not remind me. I see. If I had said, guys, please remind me, I want to take you all out, you guys were going to remind me, right? They say, oh, but you say you're taking us out. No one reminded me that I should send them questions. No one. No one said, oh, say, can you please send questions? No. But if I said, guys, we're going to Mountain Casino. When? You were going to remind me. But let's see something here. But this one is very straightforward. I wanted something that has to... I thought I got a question last week that had to do with sound. All right, look, but it's fine. Let's do content quickly. Hopefully we can finish, and then we'll have time to look through all types of questions. Is that okay? Last week we did what? Sound. Remember? Sound waves. We said sound wave is an example of a longitudinal. We defined what longitudinal wave is as well. All right, so we need to learn all of those important definitions. We said, we spoke about pitch and loudness, if you remember. What controls the loudness of the sound? The amplitude controls the loudness, while the frequency controls what? The pitch. And we said humans, like, we are humans, so we focus on humans. We can hear in a particular sound range, a frequency range of what? 20 hertz to 20 kilohertz. Anything above 20 kilohertz, a human cannot hear. And that type of sound is called ultrasound. So let's quickly start today from that sound, ultrasound. Quickly, ultrasound. All right, sound that has frequency ranging from 20 kilohertz. Wait, what is 20 kilohertz in hertz? 20,000. Remember, the K is 3 zeros. And what's the range? To what? 100 kilohertz. Humans cannot hear this. Please, that's an exam question they're going to ask you in the exam. That value, very, very important. All right, we can use ultrasound to create images. Do you know that? This is very important. Okay, let me do something here. Let's talk about uses of ultrasound. We can use ultrasound to create what? Images. Question is, do you know how? Did you do this at school? How? All right. Did you guys do it at school as well? So, when ultrasound reaches the boundary of a medium, I should actually show you a clip on that. Some of the waves, some of the sound waves are reflected. I think we spoke about reflection last week. Bounce back, which is what echoes also mean. All right. And this is converted to images. This is converted to images. So we're going to look at, just mention them, a few uses of ultrasound. But I said something. I said some of the sound waves. So not all. What happens to the other ones? If I say some, it means not all of them. So what happens? Talk to me. What happens? You don't know. Okay, I'm going to tell you something here quickly. So if I have, let's call this, or let me draw it as a box. So this box could actually be a human being. Could be a human being. That human being becomes a medium. So we're going to have a medium here, medium 1. We're going to have a source here of sound, ultrasound. Now what would happen? This ultrasound releases waves, sound waves. There, coming in. We said some of the sound waves are what? Reflected. Okay, so it means it bounces back. These ones that are bouncing back will be used to create an image. So this is a screen, and we form what? Images. So if you see somebody who's pregnant and they go to the hospital, that's what happens to them. But not all of the sound. What happens? Others will be, so some will go in and transmit it. So some are transmitted. Some will be absorbed into the medium. Absorbed. And some are what? If you notice, I mentioned 3 things. That's a multiple choice question. So take note. Some of the waves, some are what? Reflected. Some are absorbed into the medium, and some are what? Transmitted. So they can go through the medium and come out because they have high energy. Yeah, just draw it quickly. Draw it. It will come in handy somewhere someday. And while you're drawing, let me just quickly do this. Ultrasounds are safe for humans. Ultrasounds are medically what? Safe. So they are used for, what are they used for? For health, talk to me. Health diagnosis. They are used to what? Measure the heartbeat. Of a fetus. They are used to check for blockage or for meter flow, blood meter flow. So they are used for health diagnosis, treatment, measure. This is for pregnancy. This one they are definitely going to ask you. So those are medical uses. They are used to check blood flow, how your blood is flowing. So some people have what you call blood cloth. I'm sure you must have heard that before. So it means the blood is not flowing the way it's supposed to flow. The way we check that is through using what? Ultrasound. When you were small, I'm sure your mom went to the hospital, and you know that picture, that's ultrasound to see, oh, that's the baby. All right, that's ultrasound. So when you guys become medical doctors, you must remember this day that, oh, that guy taught me that. Okay. There are so many uses. When we get to grade 12, we still come back to this. Yeah, we're going to skip it in grade 11, but we'll come back to it in grade 12. We're going to use this to talk about the universe is expanding. We're going to talk about your speed trap cameras. You know, when you're running beyond the speed limit, take a picture. It's all sound. All right, so please let's know the medical uses. And I think last week I also mentioned some of the use of ultrasound. If you remember, we can actually calculate the depth of the sea. That's another one. But when the examiner specifies to say medical uses, please don't tell them that the sea. That's not medical. When they say medical, we talk about what? All of these three. To diagnose, all right, health problems, to measure the heartbeat of a fetus, and also to do what? Check for blood flow. It makes noise into my mind. All right, blood flow meter. All right, let's run to the last part of the whole thing about waves. Do you know what that is? EM. Electromagnetic radiation. Have you done that? So what did you do this week? Electromagnetic radiation. Okay. All right, so we have medical uses. Like I said, we have non-medical uses as well, right? Non-medical. Let's talk about some non-medical uses, just to reiterate what we mentioned last week. Non-medical uses. Okay, Mikhail, let me know once you're done. Non-medical uses. We just mentioned about 2 or 3. Okay. You've heard of mining. The mining. We also use it for mining. So we use ultrasound to check. If they tell you a place has natural resources and it's full of platinum or it's full of gold, you should ask yourself, how do they know? Did they start digging before they realize it's gold? Because if they start digging before they realize, then they will dig the whole place and find nothing. So how do they know that there's gold? Ultrasound. So that's one. So we have medical uses, we have non-medical uses. Quite a lot. All right. So I've given you 3 medical uses. Let me add non-medical uses of ultrasound. All right. What are the ones we mentioned last week? We mentioned one, right? What is it? Okay, well, let's do something. I want us to do something. Let's kind of create a table. Let's create a table. I know we are going to have to rewrite some information, but it's important. medical uses and what? Non-medical uses. It's very important. Medical uses and non-medical uses. So we must first mention that ultrasound is safe. Okay, I'm not going to read that one, right? It is safe, does not hurt a human. Okay. So what did we say? No. Let me give you a well-listed point. So doctors use ultrasound to check what? For the health of babies. So number one, let's say the heartbeat. Heart, H-E-A-R-T, right? Okay. Heartbeat of, it's not a baby yet though. Yeah, it's a fetus. Heartbeat of fetus. What else? All right. It's used in the blood flow meter to check for blocked arteries and veins. You know the difference between veins and arteries? Come on, natural science. No, in terms of function. Huh? Nope. Mm-mm. Some take blood to the heart, and some take blood away from the heart.
To the lungs.
To the lungs.
To the heart.
Because that's where it gets what? Oxygen.
Yeah.
And then the
Arteries take it away.
You sure?
Yeah.
Okay, but that's natural science, right? In case you want to become a doctor, you need to know that. All right. Number 3, for diagnosis, let's say health diagnosis. Health diagnosis. Okay, let's quickly talk about non-medical. I'll add more to the medical. Non-medical, measure the depth of the sea. What else can you tell me? To determine natural resources deposits. What else? Spit thingy. Oh yeah, non-medical, lovely. Okay. Speed trap cameras, speed traps. Okay. To detect, something I want to remember, I've forgotten the particular name, but to detect damages in aeroplanes. Huh? Okay, but I think if we know just this, there's quite a lot, but it's fine. Oh, let me add this one, health. It is used to detect and to destroy tumors, very important. And gallstones in the kidney. Kidney treatment. Now the question they're going to ask you is, why can it be used in human? NB. It does not damage what? Human tissues. So it's safe. Oh, non-medical uses. Let me add this one. Interesting. Bats find their way and prey on insects. Did I mention this last week? Yeah. So what will a bat do? A bat will send sound and wait for it to return. And once it returns, it knows there's a wall. So if you put a bat in this room, yet they have bad eyesight, they will not collide with the wall. Why? As they fly towards the wall, they're measuring the distance or the time of return. So when they go close to the wall, they can hear quickly. So they know there's a barrier. They turn. And if there's an insect, just get the insect. So non-medical and medical what? Uses of ultrasound. You need to, if the examiner says write 3 uses of ultrasound, you can write any. But if they say 5 medical uses, don't write bats. Don't write the sea. Don't write natural deposits. But if the examiner says non-medical, don't write kidney. That's medical. Okay, so we must know the difference between all of those. All right, quickly, let's move to the last part. Last part is electromagnetic radiation. Ijoma, are you okay there?
Yes, I'm okay.
All right, beautiful. Electromagnetic radiation. So you now is going to be ahead of your school. And these guys are writing a test on this tomorrow, so it's a good one. Electromagnetic radiation. Ijoma, tell them to switch off the TV there.
Okay.
Or you go to a quiet room somewhere so that they don't disturb you.
So I don't understand what's going on.
Here, right?
Yeah.
Okay, you will understand the next one. Don't worry. This, we're talking about waves. Okay? We're talking about waves. So just hang in there. I'm going to look at the last section, which would be new to everyone. So you will get me just now. Okay?
Yes.
All right. I know you will be lost somewhere. We good, everybody? Can we move on? All right. So there is something we call electromagnetic radiation. So this one you would get just now. Electromagnetic radiation. Just listen through, okay? Electromagnetic radiation. So I'm just going to use EM. You know, I get lazy, it's too long. So I just write EM. Now, the first thing is to understand what produces electromagnetic radiation. Don't worry, you're going to love this part. This part is so interesting because we've used it today. Electromagnetic radiation. We've used it today. In fact, we're using it now. The TV. All right. So, EM are waves produced when a charge is accelerated, that is, moved. So when we take a charge, and a charge is simply an electron, when we move a charge, we actually generate what we call what? Electromagnetic what? Radiation. I was trying to get a little check there. So do you see on the left side it says wiggle an electron? All right. If I take this electron and move it, wiggle means to move. Ooh, that's a lot of, I don't know if you see waves there. And that wave is called electromagnetic what? Radiation. Let's oscillate it. Can you see the wave? So I keep the charge. Can you see as the charge is moving, what do we have? We have waves generated, right? So that is how we generate what? Electromagnetic radiation. I want to see something here, full field. Oh, this is what it looks like. But we don't get to see all of this, but this is what it looks like. That's the electric field. What do I want to show? There's something I'm looking for.
What is field?
Okay, but you understand what I'm trying to quickly display here? I don't want you to see the whole thing. All right, can you see the waves? So that is what we call, so that's a charge that is moved. And that charge, once it starts moving like that, it produces what? Electromagnetic what? Radiation. But what is this electromagnetic radiation and how is it important? So the first thing is to know that electromagnetic radiation is caused by an accelerated what? Charge. So please take note. EM is produced by when the charge is accelerated, so it's fine. I already have it that way. Accelerated what? Charge. Okay. That's point one. Point two. The electromagnetic waves has two fields that are perpendicular to each other. Perpendicular to each other. The wave has magnetic fields and electrical fields at 90 degrees to each other. Please, very important, that's our second point. When these waves are generated, it produces two types of field, magnetic and what? Magnetic field and what? Electric field. And they are what? Perpendicular to each other. That's my second point. Point number 3 about electromagnetic waves. It also has a calculation. We're going to get there. Number 3, light waves have a dual nature. Dual means what? Two. Dual nature. Wait, let me, okay, it's fine. They act, now let's change this electromagnetic, let me say electromagnetic waves rather, instead of light. Electromagnetic waves, can I just say EM? All right. Electromagnetic waves have dual nature. They can act as a wave and a particle. They can act as a wave and a particle. they can act as a wave. So electromagnetic waves have a dual nature. They can either behave as a wave and as a particle. And we're going to look at both of them and do some calculations quickly. I'll deal with the particle once we are done. Okay, are we ready? Let's start from the wave nature. Wave nature. We start from the wave what? Nature. When we're dealing with waves, we dealt with something called the speed of a wave, right? Good. So we're going to say all electromagnetic waves travel at the same speed. Of 3 times 10 to the power what? How did you know that? Meters per second. All electromagnetic waves travel at the speed of what? 3 times 10. You don't need to cram it. You will be given that formula. 3 times 10 to the power what? 8 meters per second. You don't need to cram that. Please don't even stress. You will be given on the formula page. Okay. Electromagnetic waves can travel through space. This is very important. Can travel through what? Space. At that speed. By the way, add something to this for me, please. Let me add the symbol. C. At the speed of C equals to 3 times 10 to the power 8. Very important, meters per second. Electromagnetic waves can travel through space. And when we say space, it means it's not that a medium. Remember, particle that can travel through a vacuum. So what about electromagnetic generated from accelerated charges? Number 2, the fields, which are magnetic and electric, and those fields are at what? At a speed of what? Time. Types of electromagnetic radiation. I wish I got a pic. Okay, I'll get a picture for you. Let me do something. Before I go to types, let's quickly get a picture. I'd love to have a picture here. It's going to look colorful. Types of electromagnetic. And you would be able to see the input. Let's use this one. I'm gonna beat it to it. Come on. No. I really like this one. The one that starts with the radio waves, then the microwaves. Okay. Will this one work? Buildings, humans. No, we're not going there. Let's take this one. Lovely. Let's use this one. Save image as. It's not gonna save. Once I need to get that image. Let me see something here quickly. Okay. Let's just write. I'll get a proper image quickly for us later. Electromagnetic. I'll get a proper image, don't worry. Magnetic spectrum. Now, when we talk about the electromagnetic spectrum, we are actually looking at the different types of electromagnetic radiation. And the first one we are going to look at, all right? I want to see if I can do this. Just 1 second. We're going to talk about visible, ultraviolet, X-rays, and gamma rays. Let me see if I can do this. Yep. Okay, just wait. Let me run through before we start writing. The first one we're going to talk about are called what? Radio waves. The reason why you can watch TV is because of this. Satellite and all of that. Next one is infrared. This is what your remote control uses. That's why you can communicate with that. The next one? Huh? Are you sure? Okay. Under my radio waves, I'm going to put my microwaves. All right? You'll see what I'm going to do here. Here we have visible light. And we call this what? Raw HB. This is the color of the rainbow. Here we're going to have what you call ultraviolet. After ultraviolet, X-rays. I'm sure you've heard, everyone must have heard X-rays before. Broken a finger, broken a nail, even broken a hair. Can take the X-ray of a hair. The last one, gamma rays. All right. Things we use on a daily basis. When I said we've used this today, in fact, do you know, for you even to communicate with each other on a phone, when you make a phone call, you're using all of this. Because we use it in what? Communication, right? All right, so I'm going to give you a few properties. We're not going to waste so much time on this. I'll give you the real important things that you need to know. All right, quickly. What are your radio waves? Yeah? Huh? What are you saying? Okay, what do you understand by radio waves? It's like sound waves. Okay, first thing I'm going to tell you about radio waves. Okay, we have radio waves, we have microwaves also involved there. All right, radio and micro. Let me put that together. Radio and microwaves. Or we can separate it. One thing about them is they have very low energy, low frequency, but they have what? Long wavelength. That's what they're trying to say. Now, what is the importance of this long wavelength? These ones are used in satellite communication. I'm sure you've seen some videos on the internet with NASA. When they tell you they send what? A satellite to space. Do you know what they can communicate from space? The waves coming from space can reach us because of the long what? Wavelength. Now, let me quickly explain to you what the low energy means. Do you notice that? Because this is used for, what? Satellite communication, all right? TV, cell phones. Do you notice that when there is heavy rain, what happens to your DSTV? It tells you no signal. Because the DSTV depends on this wave, but it has very low what? Energy, so it can be disturbed. Makes sense? So it's carrying signal. Yes, there's a movie, and then there's rain. Instead of punching the face, the guy just hangs. Why? It cannot communicate further because the energy of transmission is very small. Makes sense? And then you have to wait for the weather to come down before the waves can travel through. So properties of this radio, I'm just combining radio and micro. They have very low what? Energy. They have low what? Frequency. They have very long wavelengths. And what are they used for? Satellite communications. They are used for TV transmissions. They are used for what? Cell. I moved this cable. Oh yeah, can you hear me?
Yes.
All right. So we were talking about radio waves, and we said radio waves have very low what? Energy. They have low frequency. They have long what? Wavelengths. They are used in communications. And because they have low energy, what happens? They can be disturbed very, very easily. Are we okay? Are we okay there?
Yes.
All right. So you must know the different uses of this race. I want to finish this in the next 7 minutes, and then we'll look at a few calculations. I just want to give you the main points. Okay. You cannot hear me? Okay, hold on. Can you hear me now?
Yes.
Okay, sorry. I think it's just this mic. All right. They have higher energy than what? Than radio waves. What does that tell you? It means they have what? A higher what? Okay, let me say a higher energy and frequency higher energy and frequency than what? Radio waves, radio and microwaves. What else can we talk about? They have a shorter wavelength. Do you know where they are used? They are used in remote controls. Remote control. So when you see those remote control cars, your remote control TV, it uses infrared. Some animals actually use infrared, like the snake. All right. Some animals like snakes, like rats as well. Ew. All right, so things like snakes use infrared. It's also used for night vision. Have you seen these movies where they switch off all the lights and it's like green? Yeah. Yes, that's night vision, infrared. Yes, that's also thermal as well. All right, so we use night vision goggles. Night vision goggles. Thermal vision. Do you know what thermal vision is? So, I can check if a human being is in the house. I don't know if you've seen those things where they want to check where somebody is in the house. They want to check, and then they wear those goggles, and then they don't see the person, but they see something like fire. A human walking. Those are thermal. So we use infrared for that. Okay, the next one. Humans, that's all. Human vision. That is us. That's where we belong. Human what? Vision. But if we look at this quickly, red has the longest what? Wavelength. Red has the longest what? Wavelength. Therefore, smallest what? Frequency. And smallest energy. While the last one, do you think you know the meaning of roach beef? What colors do you see there? Red, orange, yellow, green, blue, indigo, and violet. That's the color spectrum of the rainbow. All right. Which one has the highest energy here? Violet. Make sense? Red has the lowest energy. Violet has what? The highest energy. So violet has the... Let me tell you a quick way to remember this. What's the color of the sun in the evening? In the evening, what's the color? Kind of red, kind of orange, somewhere there, right? Okay. Oh, it's red, orange. What about during the day? Huh? It's yellow. Please check this. I want you to think about this. In the evening, it's about red and orange. In the day, it's about yellow. Wait, when is it hotter? In the day. So it means yellow has a higher energy than orange. Orange has a higher energy than red. Green has a higher energy than yellow, orange, and red. Blue has a higher energy. I don't know if it makes sense. Have you ever seen people that wear overalls, these overalls, and they have these shiny armbands and whatnot? You would never see red. Do you know why you won't see red? Go and check. It's not really red. It's about orange. If it's red, people are not going to see you at night because it produces very low energy. Somebody's going to bump into you. Oh, it makes sense. you would see it looks more like green. Why? It has more what? Energy, so we can see clearly. So the day you want to go and buy, don't buy the one with red. You are about to die, because when you are walking on the road, people will not see it clearly. It does not give off enough energy. That's why you would see it's green, it's orange sometimes, but green is more. Makes sense now? You'll see on the leg it's green. What do they call them? Safety wears. Let's Google one quickly. Let's Google one. I want us to see what we're talking about. So somebody saying, I don't want to do physics. Look at what physics is doing to us now. We are seeing what to buy. Somebody who is not doing physics will buy the red one. All right, ready for dying. Safety wears. Let's see something. Safety wears. Let me see. No, I don't want this, man. Okay, let's try Google. So this is the importance of learning. So you can see that this thing is very, very useful to us. Google. I need to get into calculations now. Safety wears. I hope they call them safety. I just forgot the name that they use. Or reflectors, right? But let's see this image. Check. Did you see any red? Even that last one, do you notice it's not red? It's not red. Can you look at this? Is the common one. Do you agree with me?
Yeah.
Why? Have you ever asked yourself, why is it green? Now you know why it's green. Because green has a higher what? Energy. So it means we can see it better. We can see it better than yellow. We can see it better than orange. We can see it better than what? Red. So it's the Roach beef. Make sense? Lovely. I'm actually glad. It's expensive. All right. Violet has the highest what? Energy. So if they ask you for an application, that's a simple application. All right. For making what? Safety wear. So we cannot wear the one. If I'm an examiner, I'm going to put a guy there in red and a guy and I'll say, which one would you choose? And I'll make sure the one in green is very ugly. You say, no, red because it's handsome. No, that handsomeness would kill you there. All right, next one. Ultra what? Violet. Ultra violet. What do you think ultraviolet is used for? Huh? UV lamps. Now, guys, I wanted to see something, that the energy is increasing as we move towards the side. Okay, so these ones are used for what? These ones have higher energy. Higher energy than what? Visible light. So they are used for in UV lamps. They are used for sterilizing medical equipment. They are used for sterilizing medical equipment. They are used for fingerprints. Have you noticed if you watch movies and they want to look for where people have put their fingerprints, they bring a kind of special light. First they dust it with one powder, and bring that light. What are they looking for? Fingerprints. Your eyes cannot see them. Otherwise we won't need those. So they are used for fingerprints. So these things are very, very important. They are also used to attract insects. If you ever been to a restaurant, they put those little lights on top. I don't know if it makes sense.
The blue light?
Yes. It's it's not blue. It's violet. It's ultraviolet. All right? To attract what? Ijoma, you know what I'm talking about, right?
Yes.
Good. To attract what? Insects. And do you know the beauty of UV light again? It's present in your detergents. How? Because it has very high energy. All your sunlight has it. So that your clothes look what? Brighter. Alright? Present in what? Detergents for brighter vision. Or for shining, or for glitter vision. Okay, let's stop there. I think we have more than enough use there, right? X-rays? To what? To see your bones. So this one has very what? High energy and frequency. It has a short wavelength. If I do this, you understand what short wavelength is, right? What is it used for? To take, okay, we can't say to take X-rays. We are using X-rays. All right. To see what? Broken bones. So these ones can actually go beyond your flesh. Why? It has a lot of what? Energy. It can. That's why pregnant women don't take X-rays. Lovely. It can look. It. I want us to compare X-ray and your radio waves and infrared. Radio waves have very low energy. That's why some of you even sleep talking on the phone. Because the energy that is given, it's very small. Your infrared, your remote control. I used to do it to my sister when I'm watching a movie and she's talking so much. Then I get the remote control and press it towards her. That reduce your voice. Come. Now I know it's not going to hurt her. If it was X-rays, I can't do that. If you have ever gone for X-rays, you can't just go for X-ray and be smiling. Selfie. No. You have to wear a particular kind of cloth. You know what that cloth does? It reduces the energy. So a pregnant woman is not allowed because it will damage the fetus of the baby. It will kill some because it's so powerful. And that's why you can't take X-rays every day. Right? Yeah, it breaks the tissue. So you can't go there. Selfie today, X-rays, smiling, and then next tomorrow. No. I think it's about, you can't take 2 X-rays in about 3 months or so. They have a rule. Yes, because it protects you. Every time you take X-rays, it damages something. And you can't take X-rays for long. You must be done. Because the more you are exposed to it, it causes gene mutations. It kills the human what? Tissues. All right. So we use X-ray because of its high energy. And we also use it for security checks. If you go to the airport, do you notice they don't open your bags at the airport? They don't open it. They just pass your bag through one screen. It's an X-ray. Because it has high energy, it can pierce through the casing and show us everything in your bag. Make sense? All right. Let's talk about the last one. Gamma rays. Gamma rays is a radio. This one has the highest energy. Highest what? Energy. Also highest what? Frequency as well. And it has the shortest what? Wavelength. These are radioactive. These are used in nuclear plants. So when they say there's a nuclear war, this is what they're talking about. Nuclear war. So these are radioactive rays. Human beings are not supposed to be exposed to that at all. Are we okay, everybody? Are we good? Did it make sense? Okay. Ijema, you see the importance of waves now?
Yes, because I'm a bit confused. Are you trying to say that Humans must not be exposed to the radioactive waves or the gamma rays.
Yes. We shouldn't be exposed
to the gamma rays.
Yes.
Okay.
It damages a whole. If you have ever watched a movie and they tell you there's a nuclear bomb, they can't just go in and check. They have some things they use to check the radioactive decay to see whether it's safe or not. So we can't just go. If you expose yourself to radioactive rays, boom, you are gone. Why? It has very high what? Energy. So that one destroys the bones. It destroys bones. Check if X-ray can go through the flesh to see the bones. Now we are talking about something stronger than X-rays. It destroys tissues, human cells. Yes, the humans, even X-rays can kill human cells. That's why it's not good to overexpose ourselves. Now, here is the deal. All of these are coming from the sun. That's why they tell you, don't overexpose yourself to the sun. Because the sun contains all of these waves. That's why they tell you that the early morning sun is the best. The early morning sun, vitamin D. Don't go at 2 p.m. Guys, what are you doing? I am enjoying the sun. No. You no longer enjoy. It causes, this thing overexposure causes what? Skin cancer. You didn't know? Now you know. So we are not allowed to because of the dangerous rays in the sun. Okay, are we done with this? All right. Quickly, let's put that note down. Overexposure. Then we quickly do the last part. Overexposure, or let's say the sun contains electromagnetic radiation. The sun contains electromagnetic what? Radiation. Radiation. And humans must not be overexposed. Humans must not be overexposed. That's why when you are going to the sun, what do your parents do? They put sunscreen. Do you think it's just for it's protecting you against what? UV, ultraviolet. All right? Especially because of ultraviolet what? If you have sunscreen, go and check at home, you would see they write something on it, UV. You've noticed, yeah, but now today you know that it's to protect you from what? The ultraviolet and other what? Rays. Are we okay? All right. Quickly, particle nature. That was particle what? Particle nature. Here, we're going to be very fast. Particle nature. This we're going to come back to in grade 12. All right? Particle nature. Electromagnetic radiation or waves can act as a particle. Can act as a particle. Light waves contain particles called photons. Photons for photo. And we need light for photo, right? All right. Photon is defined as a packet of energy. A photon is defined as a packet of energy. And I'm going to explain what to mean by particle nature now. A photon is defined as a packet. This is called quantum physics now. If you ever heard quantum before, quantum physics. Not the quantum of a taxi rank, okay? This is what happens with your solar panel. What we're looking at right now is a solar panel. All right? Photons carry energy which can eject or remove an electron from the surface of a metal. It can remove an electron from the surface of a metal. That's why when you buy your solar panel, where do you put it?
Where the sun.
Good. Where the sun shines. You don't say, I don't want them to steal it, guys. I'm going to keep it in the house, keep it in the room. Just rather sell it. All right? You rather just sell it. So this is what it's going to look like. We have light coming here, and we have electrons moving out. So this is light, and inside light we have what you call what? Photons. And these are what? Electrons. And this is a metal. So light is going to shine on that metal, and it will remove the electrons, and the electrons are used to produce electricity. The electrons are used to produce what? Electricity. Okay. You did all of this already? So when light shines on a metal, so that's why we call it particle nature. It is called particle nature because it can transfer energy and remove what? Electrons. So light will shine on a metal and it will remove the electrons, and the electrons are used to produce what? Electricity. Okay. This is grade 12 topic again. I was doing this yesterday with the grade 12s. Yeah. We're going to do it again in grade 12. And it's amazing. People in grade 12 forget that they do it in grade 10. You tell them, guys, well, we did this in grade 10. Like, when? It's amazing. We are going to do the basic calculation now, quickly. Let's see, we should get one question now, quickly. 3 minutes, I'm going to finish up. Then the last 10 minutes or so, we'll do one question together. Okay. I need to look for one once we're done writing. How do we calculate this energy of a photon? Again, what is a photon? A photon is a packet of what? So it contains what? Energy. Now, the energy of a photon is now calculated as this. E equals to what? HF. Where E is what? Energy. What's the unit? Joules. We write J. H is called a Planck's constant. Don't worry, that will be given to you. We'll get it on the formula page just now. And this is what? Frequency. What's the unit of frequency? Hertz. Okay? And the energy of a photon, which I explained earlier on, is directly proportional to the frequency. What does that mean? As frequency increases, energy does what? increases. Again, this is why orange has a higher energy than red. Yellow has a higher energy than orange. Green has a higher energy because the frequency is also different, right? So let's just write this. Roig Bev. Here we're going to write for R, longest wave. Okay, have you written this already? Not yet. I'll write it in conclusion. I'll write it in conclusion. E is also HC over F. H what? C. The E, oh sorry, not HC over F. HC over lambda, which is what? Wavelength. HC. Okay, we've spoken about E, right? What is E? Energy. What is H? Planck's constant. What is C? Speed of? You know how I remember? Do you remember when we started waves? We're talking about wave speed. And what was the symbol? V. Wait, can I quickly make you see? There's a difference between V and C. And both of them are talking about what? Speed. Check this. If I tell you C, what comes to your mind? Don't think physics. Just think normal. You go outside now to somebody who doesn't go to school. I say C. Okay, ocean. Think of something else. The letter C. Think of something else. I need one more thing. See, like I can look at you. And for me to see you, S-E-E, I need light. Check something. So when I see this C, is for light. Because I see. I don't know if you get what I'm saying. I see. See. Light. See. Letter C. So it is the speed of light. So don't forget, don't mix. And wait, if you see a golf and it makes that sound, ta ta, what does it call them? You see this when we put this big exhaust on our cars and you drive them, we call them exhaust pipes. There's a street name for them. We call them the vrupas. Have you heard that before? V for sound, C for light. V for sound, C for light. So this is the speed of light. What is this? Wavelength. Now the energy, I thought I would have some time, man. The energy of a photon is inversely proportional to what? The wavelength. What are we saying? The longer the wavelength, the smaller the energy. So you must mention wavelength first. The smaller the longer the wavelength, the smaller the energy. Red, longest wavelength. Lowest frequency, lowest energy. Violet, shortest wavelength, highest frequency, highest what? Energy. Quickly, and I'm done. We just look at one. Let's see if we can squeeze in 2-3 minutes to look at one question. So the examiner is going to ask us to calculate energy of a photon. They will give us the frequency. We just need to know how to use the formula and throw it in a calculator. So we're going to answer one question now on electromagnetic radiation. Let's see if I mentioned everything. I always like to do that. Let's see if everything was mentioned. Röntgen. So which one has more energy, blue or green?
No. Oh, yes. Yes.
Blue has more energy than green. Indigo or orange?
Indigo.
Indigo. Violet or red?
Violet.
Okay, let me ask you this. Which one has the longest wavelength? Green or yellow?
Yellow.
Is it green or yellow? Which one has a longer wavelength? Green or yellow? Yellow. Yellow has a longer. Because the longer the wavelength, the smaller the energy. So what I need to think quickly is, wait, which one has a longer wavelength? I need to check which one has a bigger what? Energy. Then I think of Röntgen. Oh, green has a bigger energy than what? Yellow. It means green has a higher what? Frequency than yellow. Green has what? A shorter what? Wavelength. The shorter the wavelength, the more the energy. So that's why I wrote there, the longer the wavelength, the smaller the energy. You can reverse it. The shorter the wavelength, the bigger the energy. Okay. Let's try one question just to see how it looks like. And let's see if we can, from our notes, pick up all these answers. Are we ready? Ready? Okay. Quickly, just one. Let's go fetch it quickly together. You know how I do it. I fetch it with you. So we go to any folder here, resources. Let's go to physics resource. Let's go to grade 10 paper. Let's pick 2020. Let's see what the kids in 2020 were doing on waves. Let's choose the English one because you don't know Afrikaans, even if I were to turn it into an Afrikaans paper. I speak better Afrikaans than you are. I'm joking. I'm bad at it. Oh, great. Look at this question 8. Look at this question 8. Quickly, everybody. How many marks? 12. I want us to get it very fast. And all the answers are in your note. I promise you. All the answers are in your note. Number 1. Electromagnetic radiation has a wave-particle duality. What does that mean? It can act as a wave and it can act as a particle. It's in your note when I mentioned the word dual. And I think I mentioned it there, right? It can act as a wave and it can act as what? A particle. Do you want me to show you where it is? Huh? It's there. Where? Oh, there. Electromagnetic waves has a dual what? Nature. They act as both a wave and a particle. Is that done, everybody? Okay. I told you, all my answers should be there. Number 2, arrange the following types of electromagnetic in order of what? Decreasing what? Which means we should start from the low. Okay, yeah, you're right, but don't let's mention frequency. Let's mention what? Long. Let me show you how to do it to make it easy. We should start from what? the longest what? Wavelength to the what? Shortest what? Wavelength. Now let's quickly think. If something has a long wavelength, it must have a small what? Energy. So we should start from the one with what? The smallest what? Energy to the what? Highest. Oh, all right. So which one do you think has, let's see, which one has the smallest energy? Infrared. Infra what? Red. Remember I told you about infrared, the one we use in our remote controls. Next, visible light. Can I give you a little secret? I'll show you something now. Visible light. Next, X-rays. And the highest, gamma rays. Guys, look at this. Look at this word. Look at this word. It's called what? Infra. What is the last word here? What is the first visible light? Oh, wait, I lost you. I lost you. Let me show you what I mean. Let me show you what I mean. You would love this. That's how I study. It makes life very easy for me. Lovely. Look at this. What is the last? What is this word here? Where's my? What is this? Infra. Red. What is the first color on the visible light? What is the last color on the visible light? What's the next? What's the next one? I don't know if you see the connection. If from infrared, I'll go to red. Then I go to red, orange, yellow, green, blue, indigo, violet. What's the next word? Ultraviolet. So I'm using the violet to ride on. I'm using the red. Does it make sense? So my roast beef, the one on the left is red. The next one is ultraviolet. Make sense? And after ultraviolet, what do I have? X-rays and gamma rays. Make sense? Lovely. That's how I remember. So I can answer any of these questions. Are we good, everybody? Define a photon. What is a photon? A photon is a packet of what? Energy. Did I give you that definition? Yes. Guys, look at how we are cruising. We are cooking here. We are cooking the paper. Make sense? Look at the last one. 6 marks. An electromagnetic wave has a wavelength of what? 2,5 times 10 to the... You know what how I like to do my physics? I write what I have down. So check what I'm going to do. We're finishing now. What's my wavelength? So you must know the symbol. 2,5 times 10 to the power what? 9 meters. Are we there? Calculate the amount of energy. What is that? E. Wait. I have E and I have wavelength. I gave you 2 formulas. Quickly check. Which one do you think we should use? The left one or the right one? Why the right one? Because it has wavelength. And we know our wavelength. Sweet. So what's the formula? Let's write it down. E equals to what? HC over what? All right. Problem. What is H? H is a constant. C is also what? A constant. Let's go check it on the question paper. It's right there. It's never hidden. All right. So the formula. Can you see the formula? The formulas are there. You don't need to stress. Can you see the 2 formulas? All right. Let's go to our table of constants. Oh, come on. Come on board. Come on. All right. Can you see? Can you see C?
Yeah.
Speed of light in a vacuum. What about H? Can you see the Planck's constant? What is it? 6,63 times 10 to the power negative what? 34. Do I have it now? So what do I say? What is H? 6,63 times 10 to the power what? Negative what? 34. What is C? 3 times 10 to the power what? 8. What is our wavelength? 2,5 times 10 to the power negative 9. The rest is a calculator. Do you guys know how to use your calculators? I got a big one that you cannot steal. No one can steal mine. All right, how do you guys press it? Come on, everybody, let's press it. Let's test if we are going to get the same answer. Let me wait for you. Michael, where's your calculator? Come, press it, press it. Do you know how to write the exponent? Do you have an answer? What's your answer?
7.956 times 10 to the power of -17.
You sure?
But let's see what you found of around of it. 7.96. Yeah.
Okay, let's see. Ijoma, do you have a calculator there?
No,
Why not?
it's in my room.
Okay, let me confirm your answers. So 6,63 times 10 to the power negative 34. I do mine differently. I used this last 10. Can you see this times 10 to the power? Let me show you what I did. So I have that right. 6,63. Then I pressed. Can you see already it's giving me times 10 to the power? Negative 34 times 3 times 10. Can you see that again? To the power what? 8 divided by what? 2,5 times 10 to the power negative 9. Drum roll. Let's check if you are correct, guys. That's the answer you got, right? 7, what? 9, 2 decimal places, 96. 7,96 times 10 to the power what? Negative 17. Why did they give 6 marks for this? I have no idea. I want to see. I know 1. Maybe they gave a mark here. They gave a mark here. But still, this is like they're just pouring you with marks. 1, 2, 3. I want to see how they put 6 marks because it's not making sense. Let's check quickly. Do you remember all our answers? What question was that again? Question 8. 8.4. No, okay. Let's quickly check. Everybody, let's check. Let's check if we are correct. Oh, they calculated frequency, which doesn't matter. Was our first answer correct? It has both wave-like what? Characteristics, which means it can act on a wave and a particle. Did we get the arrangement correct? Infrared, visible, X, and gamma. What do we have? A particle of light what? Energy. You can just write a packet of energy. All right, they decided to break all of their formulas down, which is not important. Look at our final answer. They are even wrong. They got 7,95 times 10 to the power negative 15. They did something wrong. I don't know what they did wrong, but oh, I see what they did. They made a mistake in the memo. They wrote 0. Can you see 0,025? When they used what? 2,5. But you look at the answer. So we used the shortcut. We didn't use E equals to HF. We used E equals to what? HC over, because we already have our lambda. If we were given frequency, then we'll have said E equals to what? HF. Ladies and gentlemen, that ends waves. But we'll do some more activities just to round it up together again next week. I know you are writing your test, but you should be ready. You should be ready. We'll do 1 hour of activity before we go to our next topic. Have a lovely, lovely evening. Ijoma, were you able to pick 1 or 2 things?
Yes, I was.
Awesome. I know you've not done this at school. You're doing something different. I think you're doing chemistry. But, yep, we will talk on how to carry you along. Okay.
Yes.
Have a lovely evening, everybody.
Thank you.
Bye.
Bye.